Okay, so it's my pleasure to introduce Assaf Rinot from Bar-Ilan University, and I hope he will tell us if Ulam was right or not.
Thank you very much for the organizers. It's a pleasure to be here, to see so many people. I promised that at some point I will tell you whether Ulam was right and right about what. Actually, Ralph already said he wasn't right. So we can vote after vote. Okay, so what is this talk about? We are writing a series of papers together with Tanma Inamdar, and the series of papers are called Was Ulam Right? So part 1 is already published, part 2 is submitted, and part 3 is now in the making. Right, so to some extent we had to go through the first 2 papers in order to decide whether he was right. I'm attaching numbers to papers just because it would be very easy for you if you are interested to actually download the papers. You can go to my webpage and put the serial number and download it. Of course, 59 doesn't exist yet, but the others do. Okay, some conventions before I start. Kappa will denote a regular uncountable cardinal. We're going to use this notation NS kappa for the non-stationary ideal. JBD of kappa is a collection of bounded subsets of kappa. That's the ideal of bounded sets. And using this, I can define what is a uniform ideal. So an ideal J over kappa is uniform if it contains all bounded subsets of kappa. Another piece of notation, E kappa theta stands for all ordinals alpha below kappa of cofinality exactly theta. And if I put the greater than theta, I just mean greater than theta. And the last notation for now is the trace of a set S. Given a set S of kappa, I can look at the trace. This is all the points. Typically, S is going to be stationary, so the trace of S are all the points beta of uncountable cofinality, where S up to beta is stationary in beta. So you should think about it as the set of reflection points of S, and we're going to say that S reflects. Again, when S is going to be stationary, we're going to say that S reflects if the trace is non-empty. Okay, and non-reflecting in the case that this is an empty set. Is that okay? Okay, some introduction. Our starting point is a very basic and useful fact of set theory. This is Solovey's decomposition theorem, asserting that every stationary subset of kappa may be decomposed into kappa many stationary sets. I'm sure that everyone in the room have used this theorem at least once to prove some theorem. It's a very useful fact. And you can come up with some variation of this theorem, and each one of them has its own advantage. Some variations we don't know are possible, but if they are, then there will be potential additional applications to this sort of theorem. So let me consider a few variations of Solovey's theorem. Variation number 1 is that you want to start with a stationary set, and you want to decompose it into non-reflecting stationary subsets, namely subsets where the trace is empty. So you start with any stationary set, and you want to somehow partition it into subsets that each one by itself is non-reflecting. Why is it useful? It tells you in particular that inside any possible cofinality, a fixed cofinality theta, there will be a non-reflecting stationary set. And I can give you an application from graph theory. You already know what a coloring number is. So Shelach proved that from a non-reflecting stationary subset of E kappa theta, you can get the incompactness of the coloring number theta plus. You can have a graph of size kappa of coloring number theta plus, where all the small subgraphs, all the subgraphs of size less than kappa is going to have coloring number less than theta plus. So this is an application of a non-reflecting stationary set. Okay, so how do we get such a thing? So for instance, there is a folklore fact, maybe due to Magidor, maybe due to others, that if you have square sub lambda, assuming square sub lambda holds, you can decompose lambda plus into lambda many sets, h tau for every tau less than lambda. Each one would be stationary, and each one would be non-reflecting. So this sort of requirement is possible. You could sometimes, under some assumptions, decompose a stationary set into number of stationary subsets, each one being non-reflecting. Of course, you cannot do it in general. If kappa, for instance, is weakly compact, then every stationary subset of kappa reflects. In fact, the trace of any stationary set will contain a regular cardinal, or stationary many regular cardinals. Okay, so this is one variation. You start with a stationary set and you want to decompose it into non-reflecting stationary subsets. How about the other extreme? How about starting with a reflecting stationary set and decomposing it into stationary set that each one is reflecting, and in fact, they reflect simultaneously, namely the intersection of the traces of these sets is by itself stationary. It's really the other extreme. Why would you want that? What kind of application do I have in mind? This is the theorem of Cummings and Forman from 2010. They proved that given a singular cardinal lambda, if you can decompose the set of critical cofinality, all points of cofinality of lambda, into cofinality lambda many sets in such a way that the intersection of their traces is stationary. So you have a partition of the set of critical cofinality into cofinality lambda many stationary set that reflects simultaneously. Under this assumption, you can manipulate any possible scale in any given product and make it into another scale which is not very good. This is a notion coming from PCF theory. And this is in contrast with a fact from PCF theory that whenever you take a product of cardinals that admits a good scale, then in fact any other scale in the same product is going to be good. So good is a property of a product. And this shows you that under this assumption, very good is not a property of a product, it's just a property of the scale itself. You can have one scale and you can cook up another scale using this partition, which will not be very good. Now what Cummings and Forman did, they showed that in L you can come up with this sort of partition. And from the partition, they got the consistency of there is a scale which is very good, and there is another one which is not very good. But what we showed in ZFC is that in fact you can always do this kind of decomposition for any triple of cardinals mu, theta, and lambda, when mu and theta are regular. You can decompose the set of points of cofinality mu into theta many pairwise disjoint stationary sets where the intersection of the traces is still stationary. Okay, so this gives you the application that previously was in L, just outright in ZFC. Okay, I'm going to go to another variation. There is a notion of a fat set. This is stronger. This is fattier than a stationary set. I want to give the actual definition. But you could ask, just like we know how to decompose a stationary set into stationary subset, you can try to decompose a fat set into fat subsets, pairwise disjoint. Why would that be useful? Because fat set is morally a set that you can shoot a club through using some distributive forcing. And if you can shoot, if you have a few pairwise disjoint fat sets and you can shoot a club through some of them and maybe keep the other ones without attaining a club, then you can use it to encode stuff. And this was used quite recently. You know, there is this huge project of Kennedy, Magidor, and Van Anen where they say, let's construct a constructible universe, but instead of using first order logic, let's use other logics. And you end up with what's called the core. So for instance, instead, if I use stationary logic when I can ask questions about whether some set of points of cofinality omega is stationary or not, if this is available for my logic, I can try to start with some V and then constructing CAA by recursion. So CAA of stage 0 is the empty set. Stage +1, you just take all sets definable in this logic. And at limit stage, you just take the union of everything. This gives you some sort of a sub-inner model. Now we know that if you use first order logic, then the L of L is the original L, right? But you can ask in this logic whether it's the case that when you compute CAA inside the CAA model, whether it's the same or maybe it's decreasing. So what Ur was doing, he used the procedure of club shooting through pairwise disjoint fat sets. He showed that for any delta, you can come up with a sequence of length delta of universes where the W gamma plus 1 is an inner model, proper inner model of W gamma when you compute it as the CAA of that model. So pairwise disjoint fat sets are very useful for encoding stuff. No large cardinals. No large cardinals, yeah, just fat sets. Okay, so we have a theorem with Ari Brodsky that assuming square round brackets kappa, any fat set can be decomposed into kappa many pairwise disjoint fat sets. Is this assumption necessary? Of course it is. There is a model of Magidor from 1982 where he's starting with a weakly compact cardinal and is getting something about reflection at Aleph2, and you can show that in this model, you cannot even decompose Aleph2 into two fat sets. So there is just one fat set in this model. Okay, and of course the strength of square kappa is nuclearly compact, so this gives you equi consistency. Okay, this is already our third variation of Solovey's theorem. Let me just give you the fourth and last one, even though there are many more interesting ones. And this one's coming from the work of Woodin on the Hod dichotomy. Woodin defined a cardinal kappa to be omega strongly measurable in Hod if you can find some cardinal theta below kappa where the power of theta is not so large compared to kappa when you compute it in Hod. And now comes the thing which is similar to Solovey's theorem. Here it's on the negative. There is no partition of E kappa omega into theta many sets where the partition lies in Hod. So this, you should think about it this way. You have two universes, like a universe V and some sub-universe W. You want a partition of some set that you have in the extension, in the bigger universe, into stationary sets, in the sense of the bigger universe, but you want the partition to lie in the inner model. This is the main issue here. And the application is some sort of a generalization of the covering lemma. If there is an extendable cardinal, then there is a dichotomy. Either no regular cardinal above it is omega strongly measurable in Hod, or every cardinal will be strongly measurable in Hod. And there is a result around it quite recent by Neria and Chayut. It is consistent from large cardinals that every successor of a regular cardinal is omega strongly measurable in Hod. Okay, so now I would like to connect Solovey's theorem to Ulam. So the first thing is to notice that Solovey's theorem, in the special case where kappa is a successor cardinal, if it is of the form lambda plus, you can actually get Solovey's theorem as a consequence of Ulam's theorem from 1930. Remember, Solovey's theorem is from 1971. And this uses what's called Ulam matrix. I'm sure each one of you already saw it at some point. So what is an Ulam matrix? Given an infinite cardinal lambda, an Ulam matrix is that you have this A eta tau. So think about it like you have lambda many rows and lambda plus many columns. And whenever you fix a row and you go over the row, you get pairwise disjoint sets. You fix some eta, and you look at all possible A eta tau. Each one of them is some subsets of lambda plus, which is disjoint from all the others. But if you go along a column, if you fix a tau and you take a union over a column, the union is almost all of lambda plus. It's a co-bounded subset of lambda plus. Yeah, it's a very impressive object. But the point for me is that you can actually prove Solovey's theorem, and even a more general version of Solovey's theorem, using an Ulam matrix. And the more general theorem is as follows. If you have any ideal J over kappa, kappa now is our lambda plus, which is uniform, namely containing all bounded subsets of kappa. It is kappa complete. Then every positive set with respect to the ideal can be decomposed into kappa many positive sets. Okay, so Solovey's theorem is just a special case of J equal the non-stationary ideal over kappa. Because positive with respect to the non-stationary ideal means being stationary, and then you compose it into positive sets, you compose it into stationary subsets. And now I would like to give you the proof. I'm not giving you the proof of the construction of an Ulam matrix, but how an Ulam matrix gives you this corollary. So here is the claim. The claim is as follows. You are given some uniform kappa complete ideal over kappa, which is our lambda plus. You are given a positive set B, and I claim that there will be a row, eta, one of the options. Remember, each row consists of pairwise disjoint lambda plus many pairwise disjoint sets. The claim is that there is one of the rows is going to shatter our positive set into lambda plus many, or kappa many, it's the same, positive sets. So the claim is that if you look at all the possible taus, there will be an eta, there will be a row. When you look at you go over all possible taus, there will be kappa many taus, where when you intersect this element of the matrix A eta tau with our B, it will be positive. So together, you're going to get kappa many positive subsets of your set B. And of course, maybe it's not really the composition, but you can take all the leftovers and put it in the first successful cell. Let's prove it. So if it weren't be the case, then there will be a counterexample, some positive set B in our J plus. And what does it mean? It means that for every possible row eta, the set of all taus where the A eta tau has a positive intersection with B would have size no more than lambda. But how many rows do we have? We just have lambda many rows. So we can take a union and we are still below kappa. We are still of size no more than lambda, right? So there are many taus that are stayed outside. Let us just pick one of them. Is it okay? Am I going too fast? Okay, I'm picking a point tau from the outside. And now, remember that the union of every possible column is co-bounded. And our ideal is uniform. So this means that this is a measure one set with respect to our ideal. I can intersect this union, which is co-bounded with my positive set, and get again a positive set. Okay, so what I did here, I decomposed B into lambda many sets. The original B is positive and, sorry, lambda many sets. And the ideal is kappa complete, namely lambda plus complete. So one of the sets has to be positive by itself, right? So there is an eta where the intersection is positive. Again, I have a positive set B. I intersect it with a set of measure 1. It's a co-bounded subset of lambda plus, which is presented as a union of lambda many sets. And the ideal is lambda plus complete. So one of these cells has to have a positive intersection with my set. So what does it mean? It means that for this eta, tau belongs to T eta, or in general, tau belongs to the union of all the possible T etas, but we took tau from the outside. So this is the contradiction. Okay, so this is how you can prove Solovey's theorem, or the more general form of Solovey's theorem for any kappa complete ideal, which is uniform. You could decompose any positive set into kappa many positive subsets. In the case that kappa is a successor cardinal. Now, it's a quite curious fact that if you interpret one of the theorems of Sierpinski from around the same time, 1932, that he actually discovered Ulam matrices, I guess, independently. I don't think he saw the connection. But he showed that under an extra assumption, assuming 2 to the lambda equal lambda plus, you actually get a better form of an Ulam matrix. You get an Ulam matrix as before, but the property now is that for every kappa complete ideal J over kappa, every positive set, there will be a row eta where in fact all possible colors tau would be successful for you. For every tau, you're going to have a positive intersection with this cell A eta tau. So there will be a row where all elements of the row just shatter B into lambda plus many positive sets. So it's a much cleaner form of a partition because there are no leftovers you have to add up into one of the cells. And this is actually quite useful because if you remember the example of the Ho dichotomy where you have two universes, this is a much better situation because it's conceivable that you have two universes, W and V. V is the bigger one. And you have an Ulam matrix lying in the inner model, surviving as an Ulam matrix in the extension. But what's the problem? The problem is that you know that any positive set from the bigger model would be shattered into lambda plus many sets in the inner model, but there are sparse cells, and you have to get rid of them. You have to somehow know who they are. And if you don't know who they are, then you don't have the partition in the smaller model. In this case, you know that all possible cells are successful, so this gives you a two-universe partition. So for instance, this tells you that if 2 to the lambda equal lambda plus, and in fact, in the two universes, you have the same subsets of lambda, then in fact, you have a partition in the smaller universe that survives the outer universe. Okay, but all of this is about successor cardinals, and Solovey's theorem is not limited to successor cardinals. What do we do about inaccessibles? Turns out that that was a focus of this question was in the focus of work of Heinel, and he was trying to get Solovey's theorem before this theorem existed, and he came up with a generalization of an Ulam matrix, which he calls a triangular Ulam matrix. So this is an illustration. We're gonna have kappa over kappa matrix. We're gonna have this kappa many rows, and if you're gonna go along the row, you're gonna have pairwise disjoint sets. So eventually, since you know this kappa times kappa, you're gonna have kappa many pairwise disjoint sets. So how do you generalize it to say something which is effectively as what we had in the successor case? So this is a theorem of Heinel. He proved that if kappa admits a stationary set that doesn't reflect at regulars, so in particular, if it is a successor cardinal, which was the original case of Ulam, or if it's just non-malo cardinal, or if indeed, maybe it's a malo cardinal, but it doesn't, there is one set which is so small that it is stationary, but it doesn't reflect at regulars. Under these assumptions, there is a matrix which is having the property that for every eta, if you keep going along this eta, these are pairwise disjoint subsets of kappa. And now the second condition is that there are stationary many towers where the union over the column, there are stationary many columns where the union is going to be co-bounded. So this is what Heinel came up with when he was trying to prove Solovey's theorem before we knew it existed. He found the right way, or in a sense, to generalize Ulam's theorem. And if you go over these two properties, you see that the same sort of application holds. It is the case that from a triangular Ulam matrix, for every J, which is a uniform gamma complete ideal over kappa, in every positive set, there will be a row eta where if you look over the eta, you shatter B into kappa many positive sets. Okay, it's again the case that you don't know, maybe some of the cells will be sparse, but kappa many of them are going to be positive. Okay, so this is very nice because this gave you Solovey's theorem before it existed, but under this extra condition that there is a stationary set non-reflecting at regulars. Unfortunately, we are reaching a dead end because you can show that the existence of such an triangular Ulam matrix is equivalent to the existence of a stationary subset of kappa that doesn't reflect at regulars. So this idea of Heinel of let me find some sufficient condition for having a generalized Ulam matrix breaks down precisely at what he was using. This is the most you can do. And if this is not bad enough, there is also a dead end for successor cardinals. And this is coming from the theory of club guessing. So I'm going to give you the minimal definitions you need. First of all, given the subset S of kappa, a C sequence over S is simply this sort of ladders. What you do for every ordinal alpha, you attach some closed subset C alpha of alpha, whose supremum is alpha. So if alpha is a limit, this is just a club in alpha, and if alpha is a successor, then you can just assume it's the predecessor of this successor ordinal. This is called the C sequence. Now, some of you may know there is a theorem of Shelach that you can get in ZFC club guessing sequences. So I'm going to focus on Aleph3. And in Aleph3, you get the following fact. There is a sequence C alpha, so there will be some stationary subset S of all points of cofinality Aleph1 in Aleph3. I'm not saying all of it, but some stationary subset, where I can attach for every element in this S some club C alpha climbing to this alpha. And you have a guessing property. Every club in Aleph3, there will be some alpha in S where C alpha is contained in this club. This is a well-known version of Shelach's club guessing theorem, but I'm going to add one more ingredient, which you can do in ZFC. You can also cook up a function from Aleph3 to Aleph1 in such a way that for every alpha in S, if you look at F restricted to this ladder you attach to alpha, this is going to be strictly increasing. And in particular, one-to-one over these ladders. Is that okay? So I'm using the usual club guessing theorem of Shelach, but I'm adding one more thing, which you can also do, is the requirement of a global map that's going to be increasing over these clubs. Okay, and now I'm arriving at the following very important ideal. This is ideal coming, as I said, from club guessing, but this is not like the standard club guessing ideal. This is if the term is relative club guessing ideal, but let me just give you the definition. The ideal over Aleph3 is the ideal of all subsets where there is a club D in Aleph3, where for every alpha in S, it is not the case that relative to this X, C alpha is inside D. If you think about what the last bullet is giving us, we know that for every club D, there will be an alpha in S where C alpha is a subset of D. But now I want it to be cofinally often not only inside D, but also inside X. Okay, so what is it? Being a positive set with respect to this ideal J means that whenever you give me a club D, not only I could find an alpha where C alpha is a subset of D, but it's actually going to have a cofinal intersection with D intersection X. It's a very important ideal. It's connected to very important open problems in colorings of inaccessible, but also successor of singulars. And let's inspect the properties of this particular ideal. The ideal is focusing on points alpha of cofinality omega 1. And because of this reason, this ideal is sigma closed. Oh, sorry. This ideal is sigma closed, right? It's countably complete. Because if you have countably many sets xi's, and the supremum at any point alpha is going to be bounded below alpha, and alpha is cofinality Aleph1, if you take a union of countably many xi's, and you can take the intersection of all the clubs witnessing this thing, then it's still going to be bounded. So this is a sigma complete ideal over Aleph3. If I wanted to use Ulam's theorem, I would actually have to know that this is an Aleph3 complete ideal over Aleph3. Then I could find Aleph3 many pairwise disjoint positive sets. However, thanks to this function f, this ideal is not even closed under sequences of length Aleph1, right? Because the pre-image of any fixed I is going to be a bounded subset locally for every alpha. So each one of them is going to be in the ideal, but the union is everything. So you can show that thanks to this function f, this ideal is Aleph1 complete, but not Aleph2 complete. In particular, not Aleph3 complete. So definitely you will not be able to use Ulam's theorem to find the partition. Okay, so this is bad news for us because we do want to find as many positive sets with respect to the relative club guessing ideal. We have very concrete applications for this thing, if possible. So yeah, we reached a dead end. Or did we? Okay, so let's think about what Ulam was doing and Heinel were doing. What they were doing is they formulated some axiomatic requirement 1 and 2 about the matrix, where what they really had in mind is the conclusion, is the lemma that you will always be able to find an eta where you shatter using eta into kappa many positive pieces. This is really what they wanted, but they came up with this very particular definition that gives it as a corollary. So think about it this way. A triangular Ulam matrix, what it gives you is you can think about it like a coloring of pairs with kappa many colors. So the pairs are this eta and tau. And sorry, eta beta, the eta and tau are going to show up like here. You will see in a second, such that whenever you give me kappa complete uniform ideal J over kappa, there will be this eta, which is so nice that for kappa many taus, if you look at the betas inside B using this eta as a fixed parameter, kappa many of them are going to give you color tau. Now, if you have color tau and different color tau prime, these are disjoint sets, right? These are functions. You cannot get color tau and color tau prime using the same parameter eta and same parameter beta. So this is just a rephrasing of what the Ulam matrix give me, but in the language of colorings. Now, if I try to rephrase what Sierpinski's improved Ulam matrix gives me, it's just this variation in which instead of saying kappa many taus, I'm saying every tau, right? Whenever I have a positive set B with respect to some kappa complete uniform ideal, there will be an eta where all possible taus show up positively often. Okay, so really this is what these guys were after. Well, maybe not Sierpinski, but definitely Ulam and definitely Heinel. So instead of doing it axiomatically and getting stuck at the level of there is a stationary set non-reflecting regulars, let's just formulate what we really want. And this is what we really want. So this is going to be our definition. So given an ideal J, I'm going to define unbounded plus. Forget about the plus, there are variations without the plus and double plus and so on, but this is what I'm going to focus in here. J theta. It precisely tells you that there is a coloring of pairs of kappa with theta many colors. So it's not anymore the case that I need to shatter into kappa many pieces, maybe just theta many pieces, depending on what theta is the relevant one for me, such that for every positive set, there is an eta where theta many taus will give you a positive set. Okay, so this is an abstraction of the corollary I'm getting from an Ulam matrix, even a generalized triangular Ulam matrix. And if I want to generalize what Sierpinski is giving me, I'm just replacing theta many taus by every tau. And this is now what I would like to really study. I would like to study principles that gives me one of these two properties. And this one is the better one, right? This is the one where I can do, for instance, two universe partitions, because the representation of the partition is very, very simple. Okay. And of course, a nice feature of the Ulam matrices is that it wasn't really depending on a specific ideal J. It was working for all uniform kappa complete ideals. So I'm going to generalize a bit the notation. Instead of putting here a single ideal J, I can put a collection of ideals. And this is just saying that there is a single witness that works simultaneously for all the ideals J in this calligraphic J collection. Okay, what's the relationship between unbounded and onto, namely the one that gives you theta many ones into all of them? First of all, you cannot do it in ZFC. There's a theorem of Paul Larsson from 2007 showing that it's consistent. In fact, it follows from PFA that onto plus over the non-stationary ideal fails if you are using Aleph-1 many colors. And if you come back to what I said about Ulam matrices, unbounded plus works in ZFC. You always can do this property for unboundedly many Aleph-1s, unboundedly many colors below Aleph-1. So we see that onto and unbounded are not the same, but we do have a theorem connecting them. We show that if you have unbounded with some class of ideals J with theta many colors, you will be able to get onto plus, provided you are willing to reduce the number of colors. So this is another oversight if you think about Ulam matrices, that they always wanted to get kappa many pieces. But if you are willing to have fewer pieces that you can all of a sudden improve it to the onto version. So it works for any regular cardinal mu below theta, including the finite ones, even though finite doesn't have to be regular, depending on your definition. Okay, so using this language, here is Solovay's theorem. Solovay's theorem is the following assertion. For every stationary set S, you can fill it out into a stationary subset S minus. It's not going to be the same S, where you do have unbounded plus for the non-stationary ideal over S minus. Okay, so this is something you can prove, and this is, of course, implying Solovay's theorem, but this is really what Solovay's theorem is telling you, truly. You can shrink the stationary set into a stationary set which is tamed, and there will be a matrix that takes care of all positive sets, namely all subsets of this given stationary sets S minus. Okay, so why do I really care about all of these colorings and all of this way of partitioning? Suppose I just know that an ideal is not weakly theta saturated. Why do I care about getting it from colorings? The thing is that the way that I really encode these colorings. So if you have a coloring C, as I said, this gives you this eta many rows. Each one is a partition into theta many pieces. And if it is the case that C witnesses onto J with theta, this just tells you that every positive set B is shattered into theta many pieces. And to represent this partition, all you need as a code is a single ordinal eta. Right? All you need to know, you have this eta many partitions, and for every positive set, one of these eta is working for you. So the representation of the partition is very, very simple, modulo the existence of the coloring. Once you have it, it's going to give you a very concise description of the partition. Now, why is it useful? It's useful when I'm doing global to local combinatorics. If I want to partition a stationary set that reflects stationary often, I need to locally partition the points of reflection and eventually have a partition representing these local partitions. And this is described here a bit vaguely. If I have a stationary set S reflecting points of cofinality kappa, and it is the case that I have onto plus, then I know that at any particular reflection point, there is a code eta telling me how to partition this stationary set into theta many stationary sets. Now, since there are so few codes, one of the codes is going to repeat itself again and again stationary often. So running a global to local argument, I could decompose a reflecting stationary set into stationary sets which are pairwise disjoint, but they reflect simultaneously. This is what you gain from this very good description of decompositions. To compare, if the coloring were to be a witness to unbounded, not to onto, then a code for a partition are two parameters. You need the eta. The eta tells you that, well, this row is going to decompose your sets into theta many sets. But now I also have to record which were the ones which were positive. So now the code is a pair eta and t, where eta is as before, but t is just telling me what are the active pieces. And now there are many, many more codes compared to what I had before. But again, maybe I'm lying in a universe where I have the same subset of theta in two universes. So this is enough to have the partition lying also, working also for the extension and lying in the inner model. Okay, but I haven't yet told you whether he was right or not. And as I said, it took us a while to figure out whether he was right or wrong. We had the title without knowing whether it's true or not, true or false. Okay, so to some extent, Ulam was right. Because one of these features of the Ulam matrices is that it's not focused on a single ideal. It's not just the unbounded ideals or just non-stationary sets. It just works for all of them, right? And we managed to prove that if you have a matrix, if you have this, let's P be one of them, unbounded or onto one of them, it doesn't matter, it works for both. If you have a matrix or you have a coloring witnessing the partition for unbounded sets, it's actually going to work for all uniform kappa complete ideals over kappa. So this idea of Ulam, of doing it somehow uniformly for all ideas without asking any properties of the ideas, just being uniform and kappa complete, he was right about it. By the way, we were wrong because we thought we had this proof in part 1 and then the referee found an error. But eventually we found the correct proof and this is in part 2. What we did do right on part 1 is also showing that this is also working for normal ideals. So if you have a coloring of the form either unbounded or onto for the non-stationary ideal restricted to some fixed stationary set S, it's going to work for all uniform ideals over the same stationary set. So in that respect, Ulam was right. He wanted a single uniform universal matrix that shatters everything. He was right. And there is a but coming. After all, they were wrong because really what they wanted is this coloring principle that we came up with, right? This single matrix that has a property that for every positive set, one of the etas work for you. They didn't want the axiomatic properties they formulated, that the union of the column is co-bounded. This is just something that's sufficient to give you what you want, but this is not really what they wanted. And we proved that the existence of this universal matrix, like what Ulam was looking for and Heinel was looking for, turns out this is equivalent to some notion coming from works on ordinals, and this is the existence of non-trivial C sequence. So I already told you what a C sequence is. You attach for every ordinal alpha some C alpha, some club converging to it. It is said to be trivial if, okay, what non-trivial would say? Non-trivial would say that somehow at level alpha, C alpha is really about alpha. It's not about something from the future. So being trivial means that, in fact, all of the C sequence has to do with a single object at kappa, all the way up to kappa. So the definition of trivial is that there is a club D where every initial segment of this club is covered by one of the elements of your C sequence. This is something that shows up in works on ordinals. It was defined in Todorcevic's paper where he developed works on ordinals. And in the same paper, Todorcevic proved that if kappa is weakly compact, then in fact every C sequence is trivial. But later on, in a work with Lambie-Hanson, we showed that if all C sequences over kappa are trivial, then kappa is weakly compact in L. But in the universe, kappa is greatly mallow. In fact, you have a diagonal reflection. Every sequence of kappa, many stationary subsets of kappa, reflected some diagonally at some inaccessible cardinal. So why do I say that after all these guys were wrong? Because if you compare, if kappa doesn't admit a Ulam-Heinel matrix, then every stationary subset of kappa reflects as inaccessible. But we found out that if you come up with really the conclusion and not the axiomatic definition, that you get diagonal reflection, which is much stronger. The strength is even different. Okay, this is for the unbounded ideal. What about the normal ideals? So there we have another theorem. Given a stationary subset S of kappa, the existence of a matrix for the non-stationary ideal over S, or as you know, it's going to work for all normal ideals over S, it's equivalent to the existence of an amenable C sequence over this S. This is a notion coming from my work with Brodsky. Maybe I don't have to give you the exact definition, but the point is that if S is ineffable, then no C sequence over S is amenable. And in L, it's actually if and only if. And here there is a conjecture, which I'm very happy to tell this audience, because there are many people working in inner model theory over here. We have a conjecture, and I really hope one of you would be interested in that, that if there is no amenable C sequence over kappa, then kappa is ineffable in L. I have some kind of evidence to try to convince you. So if one of you is interested, I'll be happy to discuss it. We believe that this is the right level. The exact strength is an ineffable cardinal. So if I sum this chapter up, what I get that Solovey's decomposition theorem, you will never be able to get it with an Ulam kind of approach, or Heinel's approach of trying to get a Solovey's theorem, because if kappa is ineffable, unbounded plus over the non-stationary ideal of kappa is going to fail. And then the number of codes you need to represent partitions of kappa, of stationary subset of kappa, is as large as 2 to the kappa. So there is no compact way to present partitions in the extreme case of kappa being ineffable. So now I would like to deal with gaps. I still have time, right? Gaps. Okay, gaps is a serious issue because we know every ideal over Aleph2 which is uniform and Aleph2 complete can be, you can decompose every positive set into Aleph2 many positive sets. What happens if the ideal is not Aleph2 complete, if it's just Aleph1 complete? So there is a great theorem of Foreman from 1998. He showed that starting from a huge cardinal, you can get an ideal over Aleph2, which is Aleph1 complete, and it's not going to be Aleph2 complete because there is no Aleph2 many pairwise disjoint positive sets in this ideal. It's not. It is weakly Aleph2 saturated. So you will not be able to improve Ulam's theorem in the sense that reducing the Aleph2 completeness assumption into Aleph1 completeness, because this is the consistency contrasting this hope. Now I'm coming back to this relative club guessing ideal. Remember, we had an ideal over Aleph 3, concentrating on the computation had to do with points of cofinality Aleph 1. It was Aleph 1 complete just because the union of countably many sets is not going to generate an unbounded subset of some point of cofinality Aleph 1. It wasn't Aleph 2 complete because we came up with this function f that prevents it from being Aleph 2 complete. So it's definitely not Aleph 3 complete. However, there is a wrinkle here because if you take unions over Aleph 2 many sets, but the union is a linear union, then this ideal is going to be closed under this sort of unions. Because, again, what could break down? If the union is all of a sudden outside of the ideal, this means there is an ordinal of cofinality Aleph 1, where all of a sudden you are unbounded in this ordinal. But if you are doing it over a linear union, you won't be able to do it in Aleph 2 many steps. It must have happened before. So this ideal is uniform. It's Aleph 1 complete. It's not Aleph 2 complete, but it is closed under linear unions of length Aleph 2, and this has a name. This is called Aleph 2 indecomposable. An ideal J is theta indecomposable if every increasing sequence of sets from the ideal, the union is in the ideal. Okay, so what happens is that basically this ideal is going to be indecomposable for every cardinal which is not Aleph 1. Aleph 1 is the only problem. Okay, so remember, I won't be able to use Ulam's theorem here, just because it's not Aleph 3 complete, but maybe I can use the fact that it is a combination of being Aleph 1 complete and Aleph 2 indecomposable. In fact, you can do that. This is from the upcoming paper. We prove that if there is a non-reflecting stationary subset of points of cofinality theta, then you get a single matrix that works for all ideals which are countably complete and theta indecomposable. So here we are managing to get the partition for the sort of ideals arising from club guessing just by switching, finding out the right version. You relax completeness to indecomposability. So we get, because for every regular cardinal lambda, the set of maximal cofinality at lambda plus is a non-reflecting stationary set, we get an improved theorem of Ulam matrix for successor of regulars. Now we get that for every infinite regular cardinal lambda, you have an unbounded this sort of Ulam matrix for the class of all countably complete lambda indecomposable uniform ideals over lambda plus. So it's a much broader class of ideals. And you do it in ZFC. So in particular, what happens for our ideal, this is a very important example, it is the case that unbounded does hold for this ideal. And if you remember the monotonicity result I gave you before, you also get onto, if you relax from Aleph 3, you go down to Aleph 2 many colors. So in fact, there is a very compact way to present partitions of positive sets of this ideal. Okay, more about gaps. Working on another problem of Shelah from 1997. in a work with Jing Zhang, we ended up analyzing some ideal arising from this problem. And we found some ad hoc result. Again, I'm dealing now with gaps. Gaps means that I have an ideal over some cardinal kappa, but it's not kappa complete. It's a smaller completeness degree. So what we ended up looking at over there, very naturally it's arising, is that you have some regular cardinal lambda, and you assume square lambda plus less than lambda, and you bump into a lambda complete uniform ideal on lambda plus. So it's not lambda plus complete, it's just lambda complete. But you have a square in the background. And we were able to use the square to show that it's not lambda saturated. And this means you could find not lambda plus, just lambda many pairwise disjoint positive set with respect to such an ideal. And the proof uses generic ultrapowers, because if you are not weakly lambda saturated, then you have a critical point going to be lambda, you have generic elementary embedding, and this is enough to get the contradiction, the collision with the square. So still, this is not optimal in the sense that you are just getting lambda many partitions, not lambda plus many, and the generic ultrapowers are not in the spirit of this Ulam project. And one more drawback is that it tells you nothing about Foreman's theorem, because Foreman's theorem, you get an ideal, which is Aleph1 complete, not Aleph2 complete. You don't get anything of the sort of square must fail in Foreman's model. If you put lambda over here, it doesn't tell you anything about Foreman's model. Square must fail in this model. So recently we found a way to come up with an Ulam type proof, which works for arbitrary regular cardinal kappa. If you have square kappa less than lambda, then you have an unbounded coloring that holds for all lambda complete uniform ideals on kappa. So this improves it in various ways. This is not limited to kappa. It's a matrix, it's an Ulam type proof, and the partition is the maximal number of colors and not just one before it. And it also tells you now that in Foreman's model, square omega 2 comma omega must fail, which you couldn't infer before. There is a connection to scales. I won't have the time to talk about scales and success of the scales for singulars, but just a curious remark for regulars. Let's look at these two collection of ideas, the collection of all ideals which are theta complete and the ideals which are theta indecomposable. So as we saw before, that this is a bigger class. All the ideals which are theta indecomposable, there may be ideals which are not complete, but still indecomposable. So this is the connection to cardinal invariants of regular cardinals. We prove that if B of theta is equal to kappa, then you have unbounded for this class J of all theta plus complete ideals. Assuming D, you actually get onto. And if B is equal to D, you can actually take care of ideas which are not necessarily complete, but just being indecomposable. So it turns out that there is a connection to this study of cardinal characteristics of uncountable cardinals. There's a question of Fyodor, which do I have the time to present? I don't have to. I can skip it. I have 5 minutes. I can do it in 5 minutes. It's about you, not about I can do it in 5 minutes. The question is how much can. Okay, let me try. Okay, I think it's a very natural question. Fyodor was asking in the 70s whether you can have a simultaneous version of Solovay. Instead of I'm giving you a single stationary set, I want to partition it into kappa many stationary sets. I'm giving you kappa many stationary sets, and you find a refinement. You find some stationary subset for every S tau. You find an S tau prime, and now these guys are going to be pairwise disjoint. So this, if it's true, it implies Solovay's theorem in the special case of a constant sequence of S tau being the same S all the time. It's a very natural question. In general, the answer is negative, because if the non-stationary ideal is Aleph1 dense, and you can apply this theorem, then this is going to get a dense family which is pairwise disjoint, which is an absurd, because you should be able to keep splitting. So this is impossible in ZFC. You could ask whether instead of giving you kappa many sets, maybe I'm just giving you theta many sets, which is just one before kappa, maybe the predecessor of kappa or any cardinal below. And this is possible. So in part 1, we proved that for every theta less than kappa, if you give me a sequence of theta many stationary subsets of kappa, I can find a refinement which is going to be pairwise disjoint. Again, in ZFC. But you can ask for more, or you can ask to do it in using this Ulam type approach, which will give you a small number of codes. There, we ended up using the hypothesis of Heinel. We show that under Heinel hypothesis, there is a way to do it, but what do I mean by that? Let me give you probably the last definition for today. Onto double plus, it tells you that there is a coloring which is being ignited now not by a single set B, but you give me theta many sets B tau. And now I find a single eta where inside B tau, positively many betas will get colored tau. So somehow the eta row manages to identify that I'm an element of B tau. So this is definitely going to give you a positive answer to Fyodor's question, because there will be an eta where inside that set you will find positively often there will be betas in B tau where the color is precisely this tau. There will be a match. You can prove in ZFC that this always fails with the maximal number of colors, but under the assumption of Heinel's hypothesis, you can just do it. Assuming there is a stationary subset of kappa that doesn't reflect at regulars, you get onto double plus for every cardinal theta below kappa. So you get quite decent answer to Fyodor's question under the ZFC limitations that there are. I'm going to conclude with an open problem. You probably know that it's a well-known open problem whether the successor of a singular cardinal could be Jönsson. That's probably going to be the topic of my talk in Bedlevo. And it's very strongly connected to these club guessing ideas I was presented. I was talking about other three, but really the most important question is what can you do at successor of singulars? So by work of Eisworth and Schellach, a negative answer to this question would follow from knowing that some club guessing ideal could be a very specific one. You could decompose lambda plus into theta many positive sets for arbitrary large theta. This is all you need in order to conclude a negative answer to this very old open problem. But of course, it's a very difficult question. And that's it.
So we finished right on time, but if there are questions, Grigor, yeah.
No. So the question was whether the answer is yes or no. I think the answer is going to be negative. I mean, my hope is to prove either this way or through another way that no successor of singular could be Jönsson. That's my hope.
There are no more questions. Let me just conclude.
Yeah.
Saying, so the first talk tomorrow starts at 9:30, and now we can thank Assaf again. There's a group picture, if I understand the gestures correctly.